Hello, everyone. What if tomorrow night, when we look up at the sky, we didn't see the moon, but instead a set of magnificent rings? Imagine billions of pieces of ice and rock orbiting Earth in a thin line, forming a colossal glowing arc across the night sky. This wouldn't just be an aesthetic change, because what we'd be witnessing is the moon breaking apart and forming a ring system around Earth, similar to Saturn's. But the real question is something like this even possible? Could the moon really break apart? These questions don't belong only to science fiction. After all, the ring systems we observe elsewhere in the universe are real, and they've formed multiple times throughout cosmic history. The idea may sound incredible, but it rests on solid physics. Orbits, gravity, and tidal forces determine whether celestial bodies hold together or shatter apart. That's why we first need to look at examples of planets that already have rings. Saturn's rings aren't there by accident. Jupiter, Uranus, and Neptune also have ring structures. All of them obey universal rules, and those rules are the first key to understanding what could happen to our moon. When Galileo turned his telescope towards Saturn in 1610, he drew what looked like ears sticking out of the planet. His telescope wasn't powerful enough to resolve the rings, and he died without ever understanding what he had really seen. Today, with modern optics, we know the truth. Saturn's rings are made of countless small pieces, each one ice or rock, sometimes just a centimeter across, sometimes meters wide. Together, they form a system only about 10 meters thick, but stretching 280,000 kilometers across, wider than the distance between Earth and the Moon, yet thinner than a building floor. That extreme thinness explains why the rings sometimes seem to vanish when seen edge-on. But where did Saturn's rings come from? Scientists believe they are the remnants of a shattered moon or debris from a collision. Maybe a moon drifted too close and was torn apart by Saturn's tidal forces. Or maybe a violent impact scattered material that remained in orbit and flattened into the thin structure we see today. And Saturn is not alone. Jupiter has faint, nearly invisible rings. Uranus has complex, layered ones. Neptune's are clumpy and broken. But all of these systems share one thing. They exist within a very specific distance from their planets. This is the zone where gravity and centrifugal force balance perfectly. In this zone, particles can orbit without dispersing, but also without clumping together to form a new moon. This brings us to the next question. What happens if a moon crosses into this zone? In 1848, French mathematician Edouard Roche discovered the principle that governs this. We now call it the Roche limit. Inside this limit, no moon can remain whole. The planet's tidal forces overwhelm the moon's self-gravity, pulling harder on the near side than on the far side. If a moon drifts too close, this tidal difference begins to tear it apart. Eventually, internal gravity loses the battle and the body disintegrates. Take Mars's moon Phobos. It orbits just 6,000 kilometers above the Martian surface, well within Mars's Roche limit. Scientists believe Phobos will shatter within about 50 million years, forming a thin ring around Mars. That prediction shows that moon disruption isn't just theory, it's a natural process that really can and will happen. Astronomers studying exoplanets have even found hints of destroyed moons elsewhere. Dimming starlight and clouds of orbiting dust suggesting that moons once existed, but now only their debris remains. The James Webb Space Telescope is capturing detailed images of distant ring systems, some of which may indeed be the relics of shattered moons. So what does all this mean for Earth's moon? Right now, the moon is about 384,400 kilometers away. Earth's Roche limit for moons is around 18,000 kilometers. That means the moon is more than 20 times farther out than the danger zone. What's more, it's slowly moving away, about 3.8 centimeters farther every year. So under normal conditions, it will never come near the Roche limit. But that safety is conditional. Something powerful enough to change the moon's orbit could change the picture completely. The most immediate threat would be a giant impact. The craters Tycho, Copernicus, and Kepler are scars of massive past collisions. None were strong enough to shift the moon's orbit significantly. But what if an asteroid 100 times larger than the Chicxulub impactor, the one that wiped out the dinosaurs, slammed into the moon at 50,000 kilometers per hour? Such a collision could slow the moon down, pulling it closer to Earth. Each orbit, it would lose more energy, creeping toward the Roche limit. Stress would build, cracks would form, and finally the moon would break apart. Huge fragments of rock and dust would scatter into orbit, gradually forming a ring system around Earth. That's one scenario. Another involves rogue planets, worlds drifting free,